These two sliding blocks just calculated pi. The heavy block slides left, the light block gets trapped against a wall, and we count every collision. Block against block. Block against wall. With equal masses, the total is 3. Make the heavy block 100 times heavier, and the total is 31. Make it 10,000 times heavier, 314. A million times heavier, 3,141. Those aren't rounded measurements. In an ideal simulation, they're exact collision counts. 3, 31, 314, 3,141. The opening digits of pi, with one more digit appearing whenever the mass ratio gains 2 zeros, and nothing here looks circular. That's the irritating part. We have a wall, 2 rectangles, and straight line motion. No wheels hidden underneath. No distance involving a circumference. Just perfectly elastic collisions, meaning the blocks bounce without losing kinetic energy. So where could pi possibly get in? Before we touch that, make a prediction. The orange block has mass 100. The teal block has mass 1. Orange moves toward teal at 1 unit per second. Teal starts still. Is 31 collisions even remotely plausible? My first guess was something like a dozen. The little block would rattle around, steal enough motion, and eventually both would leave. Reasonable. Wrong. Watch the velocity labels during the final few impacts. The motion becomes absurdly delicate, as though the system is squeezing collisions into smaller and smaller gaps. Counting explains what happens, but not why the count lands beside pi with surgical precision. To see that, we need to stop watching where the blocks are and track something the collisions can't change. What the collisions can't change is total kinetic energy. Positions determine when the next hit occurs, but they don't remember the whole pattern. Velocities do. Let the heavy block's velocity be big V, and the light block's be little v. The energy is 1/2 mv squared plus 1/2 mv squared, and every perfectly elastic collision preserves it. This expression is almost the equation of a circle. Almost. The masses stretch the two directions unequally. So scale the velocity axes, call the horizontal coordinate square root of m times v, and the vertical coordinate square root of m times v. Then twice the energy is x squared plus y squared. The system's current pair of velocities becomes a single point moving on a circle. There it is, our first circle, although pi still hasn't earned its seat. Initially the heavy block moves left, and the small block is still, so the point begins on the negative horizontal axis. When the small block hits the wall, v reverses sign. On our diagram, x stays fixed and y changes sign, reflecting the point across the horizontal axis. Clean, a block-to-block collision is less obvious. Both velocities change, but energy keeps the point on the circle, while conservation of momentum imposes the second constraint. Together, they make the velocity point reflect across a particular slanted line. Though each physical collision becomes a mirror bounce in velocity space. Wall hit, reflect across one line. Block hit, reflect across another. The blocks seem to rattle back and forth, but their velocity point passes between two mirrors. The count is controlled by the angle between those mirrors, and the masses choose that angle. That mirror angle is where the mass ratio hides. For a collision between the blocks, momentum is conserved, mv plus mv stays constant. In the scaled velocity picture, a fixed momentum traces a straight line. During one collision, the velocity point starts on the energy circle, ends somewhere else on that same circle, and both points lie on the same momentum line. Geometrically, those two conditions are exactly a reflection. The mirror itself has slope square root of m over m, so its angle from the horizontal is theta equals arctangent of square root of m over m. If the masses are equal, theta is 45 degrees. If the heavy block is 100 times the light one, theta is arctangent of 1/10, about 5,071 degrees. 10,000 times heavier gives roughly 0.5 times 73 degrees. The mirror gap becomes extremely thin. Now the collision count no longer seems so ridiculous. A tiny wedge can fit many reflections before the velocity direction escapes, but counting a point ricocheting between two lines is still annoying. Every bounce changes direction, and near the end the path becomes a little nest of zigzags. So use the standard mirror trick. Instead of reflecting the moving point, reflect the whole wedge. At the first boundary, copy the wedge across that boundary and let the path continue straight. At the next boundary, copy it again. Keep unfolding. The zigzag turns into one unbroken ray passing through a fan of wedge copies. Each crossed boundary is one collision. This is the exact turn in the mechanism that I love. The physical mess disappears, and the block's entire history becomes a straight line sweeping through equal angular slices. Now, pi isn't a visitor. We're literally asking, how many angles of size theta fit into a half turn? So the answer is almost just pi divided by theta. Almost, and the almost matters because collisions are whole events. The initial velocity points directly left. After the last collision, Both blocks must be moving right with the little block no faster than the heavy one, otherwise it could catch the heavy block and collide again. In the unfolded picture, that start to finish journey covers a half turn, with boundary crossings separated by theta. The exact count is the greatest integer below pi divided by theta. More precisely, for this setup and these masses, n equals floor of pi over arctangent of square root of m over m, test the easy case. Equal masses make theta pi over 4. Pi divided by theta is 4, but the trajectory lands exactly on a boundary, so the terminal convention gives 3 collisions. Physically, heavy hits light, light hits wall, light returns, and hits heavy. Done. For a mass ratio of 100, theta is arctangent of 1/10. Pi divided by that is about 31/52, so 31 collisions. 10,000 gives theta arctangent of 100th. Pi divided by that is about 314/17, so 314. 1 million gives about 341 times 9, so 3,141. That last decimal is almost rude. The system doesn't know decimal notation, of course. It knows an angle, and we deliberately chose masses that make that angle approximately a power of 10. But approximately isn't enough. Why does the floor keep selecting exactly the leading digits of pi instead of occasionally slipping by 1? The difference between arctangent of a tiny number and the number itself has to stay smaller than the unused fractional part. That's the next piece. The blocks don't produce pi by coincidence. They exploit an approximation whose error shrinks much faster than the digit scale we're asking for. Let x equal square root of m over m for our special mass ratios. X is 1/10, 100th, 1,000th, and so on. When x is tiny, arctangent x is x minus x cubed over 3 plus smaller terms. That cubic correction is crucial. If theta differed from x by an error proportional to x squared, the collision count could wander too much. Instead, the angular error is about x cubed, and dividing pi by theta turns it into a count error of order x. As we ask for 10 times as many collisions, the error becomes 10 times smaller. If m over m is 10 to the power 2d, then x is 10 to the negative d. Ignoring the correction predicts pi divided by x, or pi times 10 to the d. The actual value, pi divided by arctangent x, is slightly larger. For d equals 2, the rough prediction is 3014 to 959, while the actual angular count is about 3014 to 9070. Both have floor 3014. For d equals 3, the rough prediction is 34 to 125 times 2, and the correction is only about 0.1, safely inside the same integer bin. We're extracting not a rounded value of pi, but the integer part of pi times the power of 10. That's why the collision totals read 3, 31, 3014, 3041. Each new pair of zeros in the mass ratio shrinks the wedge by 10, so the half-turn crosses roughly 10 times as many boundaries. Meanwhile, the arctangent correction retreats quickly enough not to spoil the new digit. A proof must check edge cases, especially when pi times the power of 10 lies extremely close to an integer. For the familiar range, it works spectacularly, mathematically legitimate, mechanically preposterous. The geometry gives the count, but it hides how bizarre the physical motion becomes. Watch the 100 to 1 case again, this time in stages. The heavy block arrives from the right and strikes the small one. At first, the little block shoots into the wall and returns repeatedly while the heavy block keeps drifting left. Each round trip is shorter because the gap between heavy block and wall is shrinking. Then comes the middle phase. The heavy block has nearly stopped. Collision after collision transfers its leftward momentum away, and for one brief moment the big block reverses while the little one is still trapped. This is where my intuition originally broke. I pictured the small block simply draining the large one and escaping, but escape depends on relative speed, not on whether the big block has reversed. The little block keeps catching it, being thrown back, hitting the wall, and trying again. Past the midpoint, both blocks trend right. The wall collisions eventually stop, but block collisions can continue until the small block is no longer fast enough to catch the heavy one. Then the velocity point has finally left the wedge's collision, producing sector. With a mass ratio of 10,000, those phases contain 14 impacts, and many happen in an extremely short physical interval. Ideal rigid blocks can do that because a collision has zero duration and loses no energy. Real blocks deform. They heat up, make vibrations, encounter friction, and take finite time to rebound. So a tabletop version won't casually hand you thousands of pristine digits. Even the masses become silly. 20 digits would require a mass ratio of 10 to the 40th. The mathematics is exact because the model is severe. But that severity is useful. Strip away every loss, and ordinary bouncing turns into angle counting. Now run the original 10,000 to 1 experiment once more. The counter races to 314, but this time put the velocity wedge beside it. Every impact in the track is one boundary crossed in the unfolded fan. The little block hits the wall, one reflection. The blocks meet, the other reflection. Fold the fan back up and the straight ray becomes the velocity point ricocheting between two mirrors. Fold that velocity picture back into the physical system and those reflections become the rattling blocks. Same event, 3 descriptions. What looked like a strange numerical stunt is really a measurement of a half turn using an extremely narrow angle. The half turn contributes pi. The masses set the ruler, theta equals arctangent of square root of m over m. Choosing m over m as 100 to the dth power makes that ruler almost exactly 10 to the negative d radians wide. Count how many rulers fit, and the integer counter writes the first d plus 1 digits of pi. There is one more lovely reversal here. We usually discover pi by measuring circles in physical space, circumference divided by diameter. These blocks never trace a circle in physical space. Their positions only slide along one line. The circle lives in the space at possible velocities, created by conservation of energy, and the collisions reveal it one reflection at a time. So the wall wasn't secretly curved. The blocks weren't performing arithmetic. We chose coordinates in which preserving energy means staying on a circle, and then the collision rules force the system to count angular slices of that circle. The counter reaches 14. The blocks separate. Nothing else happens. But now that final empty stretch of track means something. The ray has crossed its last boundary, the half turn is exhausted, and pi has finished counting.